the need for these devices that are used in these designs for these systems, they must be characterized to as wide a frequency range as possible, so that when we use these devices in our designs, we know that they're going to perform well in those bands. So we need a full characterization, full parameter extraction models for these discrete devices that we intend to use at these higher frequency ranges now and into the future. So that's really what's driving the need, device characterization. So what best to do is to have a broadband system that covers in a single sweep from RF all the way through millimeter wave ranges. And it is for design, for generating those parametric models that are all important for the circuit simulation activities that are going to be done after the devices have been characterized in the design process of the actual circuits and components that are used in the systems. So it's very important to get accurate simulations so that we can obviously optimize the first pass yield when we start to build these mimics or these devices. So the Enritsu broadband system that's in the Unicamp lab, that is the 220 gigahertz single sweep system. So basically our flagship two-port VNA that's currently available. We also have 110, 125, and 145 gigahertz extensions in addition to the 220, but the 220 is clearly our top of the line. And it's available in 2 ports as well as 4 ports. So we basically build up these systems in a modular format so that every one of them has the same building blocks going in. And really the only thing that ends up changing will be the millimeter modules that are going to provide the frequency range. So what's inside one of these millimeter modules? Well, there's quite a bit going on. It is a full reflectometer in a package that's basically the size of the palm of your hand. It's very small. Again, that's allowing us to move it very close to where our probes are, in most cases direct connecting to the probe. So that's a huge advantage. But what's inside the module? Well, the module has to create the stimulus for what it is we're going to measure. So we have our multipliers that take us all the way up to 220 gigahertz. And in addition to that, because we're talking about a full reflectometer, we also have the receivers, both the test and the reference receivers that, again, down convert our measurements that we're taking, the reflection and the transmission measurements that we're taking, and down convert them to an IF frequency. So it's really like having an entire VNA system in a single extender. But everything else is, of course, handled in the mainframe VNA. Because it goes to 220, we had to, of course, innovate what would be the interface for that. When we're looking at 110 and 125, we're working with a 1 millimeter coaxial connector. When we're looking at 145, we're working with a 0.8 millimeter connector. But for the case of the 220, we had to take it a step further. And so here what we have is a interconnect scheme that uses the 0.6 male-female pin arrangement, where the female side is on the module interface, and whatever we connect to that interface would be a male pin. So in most cases, that would be the probe. That's where we're going to be actually calibrating and making our measurements across the full 220 gigahertz broadband range. What holds this together, of course, is the waveguide flange that we use with the alignment pins. That's very important because it's difficult at these frequencies, given the diameters that we're talking here, to design a threaded connector that would work well up to these frequencies and not be extremely fragile and possibly damaged in the process. So the single-ended system is on the left side. This is a 2-port VNA with the probes attached and probing on a calibration substrate. On the right side is a differential version. So the differential version takes 2 modules and hooks to a GSGSG probe via the same waveguide flanges with the 0.6 millimeter coax. The probes are coming from MPI, so we work with MPI. They develop the probes for both the single and the dual differential. And the typical pitches are 50, 75, and 100 micron for these frequency ranges. And then to go beyond 220 gigahertz, which also the lab at Unicamp has, extenders from VDI to 330 gigahertz from 220, and then from 330 up to 500. So there's two additional bands that extend the 220 gigahertz broadband system all the way up to 500 gigahertz using the waveguide banded approach from VDI. So we have compatibility with these modules all the way up to as high as a terahertz. So I'm just going to summarize briefly how we've addressed these challenges for measurements in the sub-terahertz range, having the modules that are not only high performance, but also small enough to be able to mount close to where it is we want to set our reference plane for the measurement is a key advantage. That, of course, eliminates additional losses and preserves dynamic range for the system. We have around 100 dB of dynamic range to 220, a little bit more up to 110. But really the most amazing part of this system is the calibration stability, how it's able to keep a calibration over a long period of time. Of course, the assumption is that the environment of the room that the system is in is also held fairly constant. But we're able to perform to 1/10 of a dB on transmission measurements or a degree phase over a 24-hour period, which is truly phenomenal, which means we don't have to worry about calibrating as often and have more confidence in the measurements that we're making. And then we also have, for active measurements, we have built-in closed loop automatic level control. So that gives you some power range that you can operate when testing devices with higher gain. You can lower the test port power accordingly to match that. The picture that I show here, this is a 110 gigahertz system mounted on a form factor probe station with infinity probes. The one in the middle is a dual differential 145 gigahertz system. So here the modules are mounted side by side with very short cables running to another form factor infinity, but this time a dual differential probe. And then the picture here on the right is the 220 single-ended system with the MPI probes, again mounted directly to the wall of the module through the 0.6 millimeter interface. And this picture here is a shot that I took at Cornell University. They have a 4-port 220 gigahertz system. And this was after an LRM calibration that we performed on wafer, and you can see the substrate down here with all the standards and a map. We could just basically move immediately from standard to standard and then wind up measuring a dual differential line. And I know it's difficult to see on the screen, but it is a 1/10 of a dB scale. So each of these boxes 1/10 of a dB. So we're actually looking at all of the single-ended through parameters and measuring essentially the insertion loss of that dual differential line. So that was truly a moment for us to see that. And what happened that really helped us here too was not only the calibration method, but also the fact that the system was completely automated. So we were really controlling our probe placements very, very, very carefully. Okay, that's basically all I have. I'm happy to answer any questions. Hopefully everything came across well. You could see my slides. One last thing I want to do. Let me just stop sharing the slides for a moment. Okay, here we go. So I was just going to switch my camera over to the probe station that I'm actually in the room here in Morgan Hill where we have a a full 220 gigahertz system set up on the probe station. And I just back off a little bit, and you can see the VNA behind is a full 4-port. So it consists of the 4 boxes that I showed in the earlier slide that provide plus the integration with the millimeter modules. So those are the millimeter wave test sets themselves. 2 of them, because there's 2 pairs of modules here. So you can see them side by side. No probes mounted at the moment, so the chuck is open here. But yeah, this is a typical setup. We have a few of these now throughout the world that are full 4-port 220. But here in Morgan Hill, we use this as a measurement services lab, so we do provide some support to customers that just want to have their devices measured here in our facility. So I just wanted to leave you with that. That's the last part of my presentation. And I thank you again for your attention and for inviting me to this session today.
Pessoal, mesa de som. Alô. Bom, desculpa pessoal, a gente teve problemas técnicos aqui. Deixa eu falar um pouquinho. A gente está inaugurando esse modelo, tá? Peço desculpas por esse momento que a gente teve aqui, mas a gente vai fazer algumas melhorias com o tempo, tá? A gente está inaugurando, parte do aprendizado, tá? E a gente quer trazer o melhor daqui para os próximos anos. Isso faz parte de toda a evolução, né? A gente começa assim. Vou chamar um pouquinho a Adriele para dar uma palavra em nome da Anritsu. A Adriele, ela é diretora da Anritsu aqui no Brasil e ela pode falar um pouquinho mais sobre os equipamentos, sobre o ecossistema que a Anritsu participa. Obrigado, Adriele.
Obrigada. Gente, na verdade, fazer um apanhado aqui, vou dar uma predominância de português, né? De falar em português para vocês, mas depois eu dou uma... Deixa eu sair das harmônicas aqui. Mas falar com vocês sobre a oportunidade, né? Acho que a maioria de vocês tem noção da oportunidade que vocês têm aqui de ter um equipamento desse aqui dentro da Unicamp. Tão próximo, né? Queria estender também um conhecimento para vocês de que a interface gráfica dele, a gente tem acesso via software, que é gratuito. Dá para baixar direto do site da Anritsu. Então, para quem tem interesse em começar a mexer, entender esse ambiente, né? Até estava falando com o Célio, que no CTI também tem um equipamento desse, com uma frequência bem mais baixa, né? Na Unicamp de Limeira também tem um outro equipamento desse, com a frequência mais baixa, né? Porque 500 GB é só aqui, mas que é o caminho, né? É o caminho natural. Ninguém começa já mexendo no 500 GB. Então, assim, para encorajar vocês a ter esse contato, esse primeiro contato, o Arno é um profissional excepcional que a gente tem na Anritsu, e agradeço o espaço, professor Hugo, de ter trazido o Arno para cá, porque é uma oportunidade também, às vezes, vocês daí, vendo ele remotamente, parece que ele está muito distante. Sessão pela manhã, que a gente comentou bem rapidinho, disponibilizei meu contato, a gente tem o José Torrone aqui, tem a Cíntia, também pesquisadora, tem bastante contato com esse equipamento, o Sartori ali atrás. Vocês estão a um contato, a Lidiane, Jeane, a um contato de distância. Se vocês tiverem qualquer dúvida, qualquer curiosidade sobre... E aí eu vou tentar, agora em português, trazer uma outra perspectiva do qual é a importância disso aqui entrar o quanto antes no mundo de vocês. Frequências mais baixas. Mas se você está desenvolvendo um componente e ele já pode entrar numa biblioteca até 220 GB, isso dá uma competitividade, uma visibilidade que nem você, às vezes, quando você está desenvolvendo, a aplicação é em 50, mas eu tenho ele caracterizado até 220. Então, haverá uma predileção pelo seu componente, ao invés de algum outro.